good to go.
All right. Hi, everyone. Thanks for coming out this evening for some like extra math, because there's not enough math in your life. So I'm gonna talk about some sort of one thread of research that I'm involved in. And I wrote down here that I'm going to talk about one particular thing with Becky Petrius, but it's kind of I don't know. I'm just going to kind of tell you like a bunch of things that I know, sort of introduction to sort of modern area of mathematics these days, and everything that comes out of that. Okay, so let's see. I'm going to talk about, so this is part of combinatorics, is part of algebraic combinatorics. That means that algebraic combinatorics means that instead of studying sort of very general classes of objects, you want to study only the very nicest objects, with all the most symmetry and all the best things, and you just try to prove very strong things about a very small set of objects. And then we have this word dynamical, which means that we're going to think about some sort of action happening on these objects, where these objects change over time, and we'll try to understand like what they do. So, okay, so here's the first example I'm going to talk about with this. So the objects I'm going to think about are, I'm going to think of a little box like this, and I'm going to stack up little squares in the lower left corner of my rectangle. And so the rules are that the boxes should be like shoved all the way to the left, and they should be not floating in space. So like I couldn't have a box here because that would be something I should have shoved to the left, and I couldn't have it here because like not only should I have shoved it to the left, but it also should have fallen down. So it's not a good thing. So this in blue is the sort of thing I like. And that's the set of objects I'm going to look at. So these are called partitions, or you can realize them as integer partitions, and here they are, sitting inside some rectangle. And I'm going to tell you a way to take one of these diagrams. So you might call this a Young diagram. And I'm going to tell you how to get a new one. And the way you get a new one is as follows. First, you're going to say, like, where could I add a box to this diagram and still have a good diagram? So like this one I couldn't have added, and this one we said we couldn't have added. The ones I could have added were the two that I put in red here. So I'm going to take the two that I could have put in and still had a valid partition. And now I'm going to throw away all the stuff I started with. And all I've got are these two red boxes, and that's a disaster. So we'll have to like add some more boxes to hold them up. And we're just going to add sort of the minimal amount of stuff that we need to hold those red boxes back up. So in this case, it's just putting back the things we took away. That won't always be the case. So I put back the things I took away here to hold up the red things, and I've got a new shape. Okay, and so this thing that I've done is the action I'm thinking about. Okay, it's some way of taking one of these partitions and producing a new one. And it has the kind of ridiculous name of row motion because one of my co-authors is a madman. So we have this thing called row motion, and it does this. So here we go. So we have this, and we have this operator. You should always sort of try to apply iterating your operators and seeing what they do if you repeat them. So pop quiz, if I take this one here and I want to do row motion, someone brave want to go on video and tell me like where can I add a new square to this? Or you can just say things out loud if you don't want your picture immortalized. I see gesturing.
Like go third from the left and then that one?
On the top?
Yeah.
This one, right? I should be able to add that box. Okay, that's the only box I can add and still have a valid shape. Okay, so if I take that and I throw away all the other stuff, what I'm going to put back in is not the stuff I took away. Because like this blue square here, I don't need that to hold up the red thing. It's bonus. So the things I put in are just that. Okay, so here is a little bit more interesting. Okay, and we're going to do it again. And here there's again only one box I can add. I can just add on the bottom row. Yeah, okay, and so I don't need very much to hold that up. Just need this row. Then we'll do it again, and I get just this one thing here. And now I'll get a very small shape. And now I've got this one, I get the sort of other domino. And now let's see, I can add a box here, or I can add a box there. So I'm going to take that and I'm going to put in what I need to hold it up, and I get this shape like this. And if you're paying attention, then like you recognize the shape. We saw it before, it was right there. So here we are. So we're back home. We got home, and we'll look at this. So this is an orbit, right? Because it's like we're going around the sun. We have this thing going around. And how big is it? It has 6 objects in it. So I had this 2x4 rectangle, and I ended up with this orbit of size 6. Okay, and so now the other pop quiz is, how do I get the number 6 out of the numbers 2 and 4? Well, you're all presumably thinking the right thing. There's only like one plausible guess, and it is amazingly correct. Turns out if you take any rectangle, so here's my notation. So this is an A by B rectangle, and I'm looking at sort of the set of all ways of stacking up boxes in an A by B rectangle. And I claim that if I do this process A plus B times, I always get home. So one of the prettiest little theorems I know. It's just like really fun to do by hand. So like, you know, if you get bored and you just want to like go off, you can just draw these little pictures. It's great to do in a boring meeting. Because, you know, like when you're here, you started here and you got over here, it doesn't feel like you're like super close to getting back where you started, but then yeah, it just happens. It's magic. Okay. Beautiful.
Can you describe the row motion operation again? I'm a little confused how it works.
Yeah, okay. So let's look at this one here, okay? So I look at this shape and I say to myself, where could I stack in one more box and still have a valid shape? And well, I can't add any of these boxes because they're already there. That's not adding. And I can't add this box because they're supposed to be slid all the way to the left. And I can't add this box because it would also want to slide to the left. And I can't add this box because that also doesn't slide to the left. So the only thing I can add is this one. That's the only valid shape to add. And so then I delete my blue boxes. And I just have this one circled box floating up in space. And I say, that's not great. I need it to be a valid shape. What other things do I need to add to end up with a valid shape? And the answer is I need to have not just this box here, but I need this other box under it so that it obeys gravity and doesn't fall down. And I don't need anything else to make it stand up. Right? So I wouldn't add anything extra to this shape. That's just enough. Right? So the minimal thing that you need to end up with a valid partition again. Okay.
So why is it after the first operation from like the starting one? Why do you still have stuff like in the top? Because I guess you're adding a square. Are you adding one in the top or in the right?
I'm adding 2 squares here. So I'm adding a square here and I'm adding a square there.
Okay. Oh, so you added in all possible locations.
You add in all possible ways.
Okay.
And so it happened that for most of these calculations, there was only actually one square that you could add. And so it sort of degenerated. But in principle, you should add all of them. And then you have to hold them all up.
Okay,
so
thank you.
From here to here, like it's getting quite a bit bigger. But then it's not always getting bigger. Sometimes it's getting smaller. Okay, cool. Cool. All right, so that's neat. So Brouwer and Shriver, they're like very famous combinatorics people these days, fairly old, I guess. They were very young at the time they did this, I would say. And I think they really didn't have any motivation for it. They were basically doing recreational math. This was like the early days of computers, and they had access to a nice big computer, and they were having some fun. And they did this, and no one really knew exactly why. but it's really pretty. And here's some more evidence that it's like a very good thing to be doing, more random pretty theorems. So if we look at this picture, and for each of these pictures, we're going to count how many boxes we used. So here I had 4 boxes, and here I have 6 boxes, and 6, and 4, and 2, and 2. Then the average number of boxes I've got is 4. And I claim that if I'd started with any other diagram inside a 2x4 rectangle, the average would also have been 4. So one example is we could start with the empty shape that has 0. The thing you get next from that is going to be the thing with 1 box. The one after that is going to have 3 boxes, I promise. And the one after that's going to have 5 boxes, and the next one's going to have 7 boxes, and then we're going to get 8 boxes, and that's the entire thing being filled in. And then we're going to go back to the beginning, and yeah, the average is 4 again. I'm folding it all up. Okay, so another weird little, cute little theorem. Okay, something very interesting is going on here. And if you have a larger rectangle, then again, all the orbits have the same average size of the number of boxes, and it's something you can write down in terms of the size of the rectangle. Well, it's exactly half the size of the rectangle is the answer. Okay, the average for each orbit is the same as the average for everything all put together. That's really how it goes. All right, so hopefully you believe that something like interesting is going on, but no one really followed up for a while, except like, I don't know, when you do in math is you try to like raise the dimension on things. And so after like 20 years of ignoring this problem, Dima van der Vlas started looking at it again. And so Peter Cameron was his postdoc mentor. And he said, well, let's do the 3-dimensional version of this. So it's going to be the same idea. It's harder for me to draw the pictures, but here's the kind of thing we're going to look at. We have some cubes instead of boxes, and instead of stacking them in the corner of my rectangle, I'm going to shove them in the corner of my like 3-dimensional room, like normal room, like the one I'm in. And again, they should like obey gravity, and they should be like pushed all the way into the corner. And the operation we're going to look at is the same thing. I'm going to look at where could I add one individual box. And I'm going to add all of those boxes that I could add all by themselves. So for me, I think there's like one going to be here, and there's one like in that hole, and one over here, and there's this hole, and that hole, and this hole, and this hole, and one over there. Looks like a whole bunch of stuff that I can throw in. So I throw in those boxes, I throw away all the old stuff, it goes away, and then I say, what do I need to have to hold up my new red boxes that are like suddenly floating in space? I got some new thing. The same thing, just in 3 dimensions, and I can't really draw it. Okay, so we can do this, and you know, you hope for like the same beautiful theorem, and this is almost that. So what they prove is that if the room you're putting your boxes in has a really short ceiling, then everything is just what you expected. So I have an A by B by 2 room. That means I can only stack 2 boxes on top of each other before I run out of vertical space. Okay, and in this case, if I do this row motion operation, A plus B plus 1 times, I always get home. Okay, and it might seem like there's an off by 1 error, but there really isn't, because if I think about A by B by 1 rooms, that means I can't stack any boxes on top of any other boxes, so I'm basically doing the 2-dimensional version. So it's really the A by B by 1 room that was giving me A plus B. And so it's not unreasonable, A by B by 2, I should get A plus B plus 1. Okay, it's sort of the right thing to have here. Okay, so that's sort of, I don't know, it's weird, but probably they just like didn't work hard enough. They just couldn't get past 2 because they weren't really trying. Like obviously there should be like this general thing. You should take an arbitrary room, A by B by C, and you should do it A plus B plus C, I guess like -1 times, and you should get home. And it's a pretty good guess if you take the empty pile of boxes and you do this operation, you'll get home in exactly a plus b plus c minus 1 times. That's pretty nice. And actually, if you write down basically any random object that you feel like, and you just try this out, you just like play around with it, you'll see that this is correct. Okay, you can sort of verify it all over the place. Okay, but it's wrong. The smallest example is this. You look in a 4 by 4 by 4 box. Okay, it's not that huge. 4 plus 4 plus 4 minus 1 is 11. So you expect orbits of 11s. And there are many orbits of size 11. There are thousands and thousands of orbits of size 11. But then there's also a couple of orbits that are size 33. And okay, so that was the end of our guess. We were a little too naive. But the number 33 isn't just like any number. It kind of has a sort of 11 flavor to it, right? It is 3 times 11. It's not something completely unrelated to 11. And so they made this bizarre conjecture. They said, well, the thing we were hoping for wasn't true, but like suppose the number we were expecting to get was a prime number, like 11. Well, then they say, maybe I don't get back in 11 times, but wouldn't it be nice if at least I got back in some multiple of 11 times? Okay, like 33. Okay, so we're not going to get some random orbit size. We're not going to get a 34 or a 35, but we might get a 33. We might get a 44, but we don't for some reason. Okay, so, all right, very strange thing. And so there's evidence for this because you can compute a lot of stuff, right? Computers were better by the 90s. You could actually compute quite a lot. And actually they could prove a sort of asymptotic version of it. This is saying if your ceiling is really tall relative to the area of the floor, then you win. So if you're in a really tall cathedral ceilings sort of situation, it's all okay somehow. Okay. So I don't know. This conjecture bothered me for a long time. And so this talk is a story of how I eventually proved this conjecture. That's sort of where it comes from. All right, so here we go. Let's say what else we can say. Oh, so what we're going to do is we're going to forget about that entire story and think about something else entirely different. We're going to think about a different kind of object, and we're going to think about a different kind of operation on these objects. And something else is going to happen. So again, I'm going to look at grids. In general, I could be looking at sort of any of these partition shapes, but I'm just going to look at this. Well, here it's a square, but I'm going to look at some rectangular shape, some rectangular grid, and I'm going to number the boxes 1 up to a times b, and I want them to be increasing going this way, and I want them to be increasing going that way. So you read along the rows, things go up. You read down the columns, things go up. Okay, and you might, I don't know, these show up in all sorts of places. In particular, like, well, for me, you find them in algebra if you say, if you've been doing a lot of algebra recently and you've been thinking about groups and you've been thinking about representation theory, if you want to like take representations of the general linear group and you want to take tensor products of them, you got to deal with these objects. They're telling you all of that. And if you want to think about algebraic geometry and some cohomology rings, you got to do your calculations with these objects. They show up all over the place. And I'm going to tell you how you take one of these objects and you get a new one. So the story here is that here's my Tableau. This is called a Tableau. I'm thinking of it as an office building, and I'm looking at it from the side. And so each of these numbers, each of these boxes is like a cubicle where the poor office worker has to go live. And the numbers represent people in this company, and the smaller numbers are the more senior people. So like person number 1, this is the CEO, and person number 2 is like vice president of something. Person number 3 is vice president of I don't know what else, and person number 9 is some kind of like co-op person. And well, this building on one side, it's got this beautiful view of the beach, and on the back side, you've got this beautiful view of a dumpster at the back. And so, these increasingness relations reflect the fact that you would prefer to be on the beach side of the building if you can get away with it. And also you would prefer to be as high up in the building as you can manage because you want to be really far away from that dumpster because it's probably really smelly. So, okay, so that's why we have these two inequalities going on here. All right, so it turns out that being the CEO of a company is like a really exhausting job, which is why we don't do that, which is why we do math. And so like eventually you retire and this company lost their CEO. So what are we going to do? Well, we need to replace the CEO, and we could like hire from some other company, but we're not going to do that. We're going to like just promote people inside the company. And so we're going to find somebody to take the CEO's place. And the rule is it should be someone who like used to report directly to them. So it's going to be either the person to the right or it's going to be the person below them. And well, which one should it be? It should be the one that keeps the seniorities correct. If person 3 tried to take over the job, then like they would be bossing person number 2 around. And that's wrong. So it's got to be person number 2 here. I'm going to take the smaller of the 2 available people. Oh, I forgot. First, I'm renumbering everybody. I just took 1 off of everybody because 1 was gone. Okay, and now I'm going to do this thing. Okay, so person number 1 slides into the new CEO spot. And now who's going to replace person number 1 right here? Well, person 3 is in competition, person 4 is in competition, and we're going to choose between them. You might think person number 2 should win because they're the smallest number, but they don't want to go that way because that way is back towards the dumpster. It's up, but it's also towards the dumpster. No one wants that. So person 2 is like quite happy where they are. Okay, it's just person 3 and 4 that are going to compete. And so person number 3 is the one who takes it. And now we have this empty job in the middle, and people 6 and 7 are competing for this job, and number 6 wins because they have a smaller number. And then this job isn't that great. Only 8 is a candidate, so 8 will take it. And then this job is a terrible job. No one wants it. So we'd better like make some kind of outside hire. This is an entry level position. Here's some new person, number 9. They can live next to the dumpster. Okay, so we've done it. We've fixed our company. All of our cubicles are filled. We have a new CEO. So we took one of these objects, one of these standard Tableau, and we produced a new one. Okay, new operation. Okay, so this also goes back to the 70s. This work of Schützenberger. This, it looks like a German name, but he's French. So Schützenberger. And he maybe proved this theorem, though I don't think he wrote it down anywhere. He says that this operation also has some really nice dynamics, some really nice orbit structure. If you do this thing, so we've done it once, if you do this thing 9 times over, you'll get back the one you started with. So in general, you have any size rectangle you want. You do it once per employee, and everything comes back into place. Okay, so here's a picture that I didn't really space things out quite right. So here's the one that we started with, and here's the thing we just computed. And I computed some more of these, and you'll see that there are 9 of them, and they make this nice little orbit. And 9 is coincidentally the number that you see in this corner. There. Okay, so this is another fun game to do in a boring meeting, because you can really do this by hand. And again, it feels pretty magical when you're around to here and you're like, I don't feel like I'm getting back at all. I think I probably made a mistake, but then you just go a little bit further and you didn't make a mistake. It actually all works out. It's pretty exciting. Okay. So I don't know. I mean, I look at these and it just feels like everything's sort of flailing around wildly. It doesn't feel like I'm getting back around in any organized fashion, but I am by magic. Okay, so Okay, so here I've told you two different stories, and they seem like they have nothing to do with each other. And they pretty obviously have nothing to do with each other. We have two different kinds of objects, and we're doing two different things to them. And you know, they both have some nice properties, but whatever. Okay, so this operation, like I said, you can do it in representation theory, but it also like shows up in algebraic geometry. Like you want to do some, you like take your geometry is really hard, and you're like, gosh, I wish my geometry was just some algebra, because maybe I could do some algebra, but gosh, my algebra is really hard, I can't do that either. And then you're like, well, I guess maybe I could turn that into some kind of game of sliding boxes around. And if you slide the boxes well enough, then you know what the algebra is, and you know the geometry, and it's all great. You want to compute this stuff. So this is how you go about computing a lot of these geometric properties. And there are like better versions of this geometry that you do nowadays, right? All these famous algebraic geometers in the 70s and 80s, right? They told you how to do better versions of this, and it's still too hard. Like it's even harder. So you still have to turn it into sort of sliding games. And it turns out you can get an analogous sliding game that does this like richer, fancier geometry, scary stuff. It's not so bad when you turn it into combinatorics. The only change is that now I'm going to have employees, like employee number 4 is going to have more than one job, because you know, maybe they don't pay very well, so you just gotta hustle. So person 4 takes 2 jobs at the same time, and so now we still have these increasing conditions, and we're gonna do the same thing. We're gonna get rid of the CEO, and we're gonna sort of slide everybody up into the corner. And the change is that like it might be the case that you have this empty job to fill, and you have 2 candidates for who might fill the job, and the 2 candidates happen to be the same human. Well, then it's like pretty clear who should win. Like you take the job, and then like your old jobs are both empty. Because your new job just pays so much more. You're just happy to give up the old jobs. I mean, you have to give them up, because otherwise you'd like be your own boss, and that's like inappropriate. Okay, so then you could have the situation where you have multiple empty jobs. You could be like this. Here I have 2 empty jobs, and maybe I'm the best candidate for both of these empty jobs. Well, I'm really greedy, so I'm just going to take both of them. Okay, I'm just going to go take both those jobs, and I just vacate over here. So you can like make this formal, but stuff. You just had a sort of slightly more complicated sliding game. Okay, and that theorem was so pretty. Like we want to like prove it again. We want to do it in like extra generality, and so I tried to do that. Right, you're going to take some rectangle and you're going to fill it up with employees, but like some of your employees have multiple jobs, and you're hoping that if you do this operation like a nice number of times, you'll get back where you started. And I think it's not clear whether the right number of times is number of boxes or number of people, but it turns out it's number of people. Right, before that was the same, and now there's fewer people than boxes, but okay. And so I proved like some sad version of this, which is that if your office building you know, looks like this and it only has 2 stories, then that's true. If you do this promotion operation once per employee that you have, you always get back home. And that, I don't know, that felt okay. And in case you don't believe that something cool is going on, here's like an even better version of this. So here's some super magic stuff. Let me define some polynomial. So I'm going to take the number I, and I don't like the number I. It's an integer. I'm going to turn it into a polynomial, and it just turns into this polynomial. So this polynomial has the property that if I set q equal to 1, then it just becomes the integer I. The polynomial has I terms. Set q equal to 1, they just all become 1. It's 1 plus 1 q times. Okay, so you can do that, and you can define some sort of polynomial version of the factorial operation. You just take the normal formula for factorial, and you put q's on everybody in sight. There's some huge polynomial, looks terrifying. And you can also get a q binomial coefficient if you just take the normal formula for binomials and you put q's on everything. It looks like, so this is some polynomial on top and some giant polynomial on the bottom. It looks like a rational function. but I promise it's not a rational function. Like actually everything cancels. It's actually a polynomial. Even better, it's a polynomial where all the terms have non-negative integer coefficients. Which means it looks kind of like a generating series, and actually it is a generating series. It's actually counting, it's counting those piles of squares that we had in the beginning, according to how big they were. So we get this nice generating function. And here's some magic. So let me take this ratio of some binomial coefficients. Also looks like a rational function, but I promise it's actually a polynomial. And it's also a generating function. And what we do in generating function land is we have q. Q is a dummy variable. You're not supposed to like evaluate that stuff. If you evaluate it at 1, you're just counting the set, but you're not supposed to evaluate your generating functions, but we're going to do that anyway. So let me take like this, you don't have to understand any of this. Let me take some complex number that is a root of 1. So I take some complex number that if I multiply it by itself 2n minus k times, I get 1. And I take this complex number and I shove it into this generating function for q, and I expect some sort of horrifying complex number to pop out the other side, but I don't get some horrifying complex number. I get an integer, and I get not just any integer, I get a non-negative integer. And not only do I get a non-negative integer, but it's counting things for me. It's telling me exactly how many of these combinatorial objects came home in exactly that number of steps. So nice things going on. Very, very nice. Yeah. Okay, when you get results like this is called cyclic sieving. How do you spell sieving? I before E. It's always a hint that there's like some secret representation theory happening somewhere. If only you could find it. All right, so amazing. There's that. So we had this nice theorem for arbitrary rectangles where every employee has one job, and we had this theorem that I came up with for very short office buildings where people have multiple jobs. And it's obvious like how you should try to glue this together into one big theorem. It should look like this. You should take arbitrarily shaped office buildings and you should let employees have multiple jobs. And you should do it once per employee and you should get home. That should all be very nice. And it's great. You can write down sort of any example you want, just sort of like write one down, and you can compute it, in your boring meeting, and it will work. Like pretty much guaranteed it's going to work. But unfortunately, the theorem's not true, or it's not a theorem. It's not true. Here's this nice corporate hierarchy. Here, this Tableau. It has 11 employees, and well, there's 16 jobs, but only 11 people working them. So we think that if we do this 11 times, we should get back where we started. And we almost did. Like this thing over here is almost the same as the thing on the left. I just marked in red the part that's wrong. Pretty close. And it turns out that in order to get back where you started, it wasn't 11 times you had to go, it was 33 times. So so we spent a while, after I found this and there was this other problem, we spent a while just sort of like running into each other and being like, I had this number and I wanted it to be 11 and it was 33 and I was sad. And like they would say, I also had this number, I wanted to be 11 and it was 33 and I was also sad. And then, we would go our ways. And then finally, what happened was we, went to one of these meetings where they like lock all the mathematicians in a room for the week and make them talk to each other, like the sort of thing that doesn't happen these days with everything being online. And we actually checked the numerology, and it didn't take all that long for us to realize that we were clearly studying the same thing because the numbers worked out everywhere. And once we knew that that had to be the case, it wasn't really that hard. So here's sort of how this works. So somehow these are secretly the same story. So here's my pile of cubes. My pile of cubes doesn't look like the right kind of object, but it really is. So I'm just going to take it, I'm going to sit on it, and I'm going to squash it down into the floor. And over every tile of the floor, I'm going to record how many boxes I squashed. So like these stacks here, those are stacks of 4, and they give me these stacks where I have 4, and over here I have no boxes, and that corresponds to these zeros. So it's sort of clear, like rotating and squashing and counting boxes. And this looks kind of like the right thing because at least it has numbers in a grid, which is progress, but they're decreasing instead of, they're decreasing instead of increasing. So I just like spin the whole thing around, and now they're increasing. And the problem is that now they're less than or equal to, and I want them to be strictly less than. And that's not so bad either. Like I'm just gonna like add 1 to this stripe, and I'm gonna add 2 to this stripe, I'm gonna add 3 to this stripe, and 4 and 5 and 6 and 7, and I just get these other numbers, right? Things that could have been equal are now like definitely separated from each other. Okay, so this is some way of taking one of these objects and producing one of these objects. But certainly not clear that like the operations we're looking at have anything to do with each other. And they almost don't. So here's a commutative diagram. And you're young, so you're supposed to be scared of commutative diagrams, and that's okay. I'm just going to read it to you. I'm going to tell you what it says. And as we read it, we're also going to cheat, and we're going to pretend that right here it says row motion. And it doesn't say row motion, but like, let's just wish it did. So what it's saying is if you take your pile of cubes that you have here, what you can do is you can take your pile of cubes and you can sit on it and get one of these Tableau. You squash it down, and you take your pile of take your Tableau, and then you promote your Tableau, and you get some new Tableau. You go like this, and you go like this. Okay, and the other thing you could do is you could start with your pile of cubes, and you could do row motion to it, give you a new pile of cubes, and you could sit on that and squash that down. And what this is supposed to be saying is that it didn't matter which one you did. You can either squash it first and then promote it, or do the row motion operator on the cubes and then squash it. Okay. So if this were true, that would be really nice because it would tell us that the orbits all match up on both sides because everything, well, it's exactly the same. So if you have an orbit here of size 12, then over here you also get an orbit of size 12. So it gets carried through. Okay, unfortunately we cheated because it didn't actually say row motion. But you kind of win. So it turns out there's not just this one row motion operator, there's lots of operators. You can you take your big room that everything's sitting inside, and you like pick a bunch of parallel planes to slice through it. And you can slice them sort of by any angle. You just sort of pick anything you want and you slice according to that. And every way of slicing is going to give you another operator. And they're actually different operators, like they do different things to your piles of boxes, but they actually all have the same structure, right? If one of them has an orbit of size 33, then they all have an orbit of size 33. Okay, and this is some algebra to check that that's true. And one of these operations, one way of slicing gives you row motion, the thing we wanted about, and some other way of slicing gives you the thing that showed up on the previous slide. So it's kind of interchangeable. So there is some way of like actually matching these things up. It's not quite as nice as just sitting on them and squashing them down, but there is something you can do that makes it all match up. Okay, so we kind of win because it's not exactly explaining like why we're getting 33s when we wanted 11, but at least it's clear that like the reason why the one group of people has 33s instead of 11 is the same reason the other people have 33s instead of 11. It's because it is all one problem. Right? Two different sides of the same problem. And you get some cool stuff just by like pushing things back and forth across this. So we started with this theorem that I like so much of Brouwer and Shriver. I said it for A by B rectangles, but that's the same as A by B by 1 rooms. And we said the order was A plus B. You always got home in A plus B. Well, if you use this bijection, that's telling you that you could just as well be studying Tableau. So there's like corporate hierarchies where the building has only one floor. So it looks like this, and it's got a bunch of employees sitting in it like this. And it's not very hard to figure out the dynamics on Tableau that look like this, because like nothing really, it's like a Congo line, right? You lose the CEO and everyone just like shuffles to the left. And like, that's all that can possibly happen. So it's like not very hard to see that the order of the action over there is like not very complicated. Okay, so the Power-Shriver theorem ends up being equivalent to this like pretty simple statement, like once you believe this bijection. And then there's another cool thing you can do, because when you took your pile of cubes, you could squash it into the floor to get a tableau, but you could just as well have squashed it into the side wall or like into the other side wall. You have like 3 different directions to squash things, and they all give you Tableau, and they all do nice stuff for you. And so if you squash it the other way, you end up with a different result entirely. It gives you a result for Tableau of arbitrary rectangular shape, but where you have very few employees, where like everyone in your company is super overworked. Right? Everyone has many jobs. And in that case, again, if you do it once per employee, you win. Okay, and to this day, it's been 4 or 5 years. To this day, I don't know any other proof of this fact. I don't know like a direct proof. The only way I know how to prove this is you like shove it through the bijections until you win. But somehow like there must be some, it's like a very concrete thing with these Tableau. Okay, and so we can do the same thing with these like height 2. Where you have a room of height 2 and you're stacking up your boxes, right? This theorem of Cameron and van der Vlas, that the order was a plus b plus 1, that turns out to be exactly the same as the thing that I worked so hard to prove about my little Tableau with 2 rows. It's just really the same thing. So, okay, so in some sense, if you knew the bijection, you already knew the thing I worked hard for, because it was already Cameron van der Vlas. But you can also do the same thing again, where you squash it into the sidewall instead of the floor, and you get this other theorem about Tableau of arbitrary rectangular shape. And again, not very many employees, but not quite as few as last time. You get 1 more employee than you had last time, and it's still okay. You do it once per employee and you get home. Okay. Okay, so you know some stuff. And the other thing that comes out is, remember we had this weird conjecture of Cameron and van der Vlas. They said, like, if the thing was prime, then we're hoping that you don't get back in that many steps, but you get back in some multiple of that many steps. And they proved it in the case that the ceiling was really tall on the room, and it was some sort of weird technical condition on how tall was tall. And it turns out if you take sort of pretty trivial facts about Tableau and you push them through the bijection, you get exactly this. You get exactly this weird number they wrote down. And the question of how tall is. So that's a little surprising. But if you work harder, and then we worked quite a bit harder, if you know some more stuff about Tableau, then you can push that through and you can do a little bit better. So here's a slight improvement on what they did. The ceiling doesn't have to be quite as tall as it was before. We've brought it down by roughly a factor of 1/3. Okay, so still true for slightly taller ceilings, that maybe you don't get what you want, but you get some multiple of what you want. Not the best, but it was like the first progress in 20 years. And so I felt okay having done that. Okay, but then I didn't know what to do. I got stuck. I was very stuck. Couldn't figure out what was going on. But it turns out, like, anytime you like rectangles in your life, you're supposed to think about these other shapes too. So instead of like, your floor plan being rectangular, you're in some kind of weird postmodern building where the floor of the room is like shaped like this. Okay, it's just sort of a funny art gallery thing. And so again, you're just going to like stack your boxes like up into this corner in some kind of way. Okay, so it's this room, but then it has walls that go straight up and you stack your boxes in. Okay, so you're supposed to think about these 5 different things and think about what's going on. And again, so there were these conjectures about stacking boxes in these shapes, and it seemed like there was like no way to deal with them, except finally we knew you could turn them into Tableau, and you could work with the Tableau instead. And the Tableau are just much nicer in so many ways. And so there are these strange conjectures of Rush and Shi about these weird shapes. And we turn them into statements about Tableau instead, and it turns out then they're not so bad. So you could prove them for these two things, and you could almost prove it for this one, except it wasn't true anymore. These are also results, of the form take some giant polynomial, stick in roots of unity, and it will tell you everything you want to know. And it really does tell you everything you want to know about the blue shapes, and it tries to tell you stuff about the red shape, but it fails. So Rush and Shi, by the way, were undergraduates when they made these conjectures. It's like one of the best undergrad papers I've ever seen. Rush, they both went to MIT for graduate school. Rush continued working on sort of similar stuff in grad school, and but then went into finance. And she is a topologist now. Good stuff. Okay. And then I didn't know what to do. But then I had a dream. I woke up one morning and I had this thought that, when I looked at this Tableau, and I did it 11 times and I didn't get back home and I was sad, the failure wasn't just anywhere. The failure was here, like in the middle of the Tableau. And I had this idea that maybe it was always in the middle, like maybe around the boundary, this like frame shaped thing, maybe it was always okay around the boundary. And I just had this thought when I woke up that if I could prove that somehow this would solve that Cameron von der Slaes conjecture that I wanted. And so I was pretty excited. Like you have a lot of ideas while you're sleeping, but usually they're terrible ideas. Like when you wake up, they don't make any sense. But this time it actually worked out, because it is in fact true that when you do the promotion once per employee, you don't get the same picture you started with, but it is the same around the boundary. It is the same on this frame. All the weird stuff happens in the middle. Okay, and I could prove that. I was hoping this would then just give me the thing I wanted, but then I got stuck again. So the first part of the dream worked out. I could prove this thing. I didn't really know why I wanted it. I just wrote down this weird fact, and I got some of these weird statements about like average values being the same on stuff, and I packaged it up and was done for a while. Okay, but it turns out that really was my dream. My dream was good. My dream was better than I was. It really is exactly what you need to prove it. And so then I started talking with Becky Petrius a few years ago, and so we can prove the following. And so the following is sort of the right version of this conjecture. So I'm supposed to look at my Tableau and look at the size of the orbit. This orbit has some size. And I don't know what that size is. I can't tell you like what number it's going to be, but I can promise you it will never be relatively prime to the number of employees. Okay, and so in particular, if the number of employees was a prime, then K had better be a multiple of that prime, because there's no other way for that to happen. So this is like the right way to state their conjecture without the strange condition on primality. That's what's going on. Okay, and once you have the right statement down and you know this thing that I dreamed about, then you win, and it's not actually that bad. So like imagine that these two numbers were relatively prime. We're gonna get some kind of contradiction. Well, what happens is like, here's my orbit. Here's all the different things around my orbit. And here's my original thing, T. And what we've learned is that the previous thing told me that if I go Q steps along this orbit, if I promote Q times, I'm going to get some other thing over here, but it's going to have the same boundary. And if I do it again, I go another Q times, I'm going to get something else. And it also has the same boundary. I didn't change the boundary. I didn't change the boundary again. And I just keep going. And I'm like, in each of these steps, I'm not changing the boundary. But because the size of this whole orbit is relatively prime to Q, this is like some elementary number theory thing, which is like, it's a statement about like generators or a cyclic group. The point is, if I just keep bouncing around by Q, I eventually hit everybody before I get back. I hit everybody here. And so what we learn is that actually everybody on this entire orbit has the same boundary. Every single thing has to have exactly the same boundary. And so in particular, this tableau that I started with and the like very next thing, this promotion of T, like they also have exactly the same boundary because of this thing about cyclic groups. And so then you have this tableau whose boundary is the same as that of its promotion. And you think a little bit about like how promotion works. It's not so hard to work out that it's like is not a thing that can happen. It's just impossible for the frame to stay the same as you do that. Okay, and so you win. So there's a contradiction, and so therefore it wasn't really the case that they were relatively prime. So you win. Okay, so their corollary, in the case that you're prime, everything is going to be a multiple. So the trick was take their thing about piles of boxes, turn it into a statement about Tableau. That's trick number one. Trick number two is think about these frames. And you win. Okay, so we proved their conjecture, and I'm very happy about that because I've been trying to do it for a long time. Okay, and so I'm almost done. But anytime you like rectangles, you're supposed to also like these other shapes. And so things that are true for rectangles are supposed to be true also here. And indeed, that works out. If you take piles of boxes in any of these shapes stacked up in rooms of with these floor plans, and you look at the orbit sizes, they might not have the size you expected them to have, but they will not be relatively prime to that number you were expected. Okay, so some sort of very strange condition on how big things can be. The proof is not the best. The proof is by looking at each of these 5 things separately and writing down a separate argument for each one, which is not the right way to do it, right? There should be some sort of general thing that takes care of them all, but I don't understand what that is. Okay. You might wonder whether like, am I proving it for these 5 shapes and like actually it's true for like basically every shape? And I was just like looking at these because I was silly, but I did some systematic looking. It's true for basically nothing, right? It's true for these 5 things and like basically nothing else, with the exception of the following. So there are these other shapes that, for reasons that no one really understands very well. So these things up here, these are called minuscule, not because they're themselves small, but because they're related to some kind of algebraic thing that is like sometimes small. These things are not minuscule, these 4, I mean, but they somehow like pretend to be combinatorially. In the sense that like when you prove a theorem that holds for these 5 things, it's often true for these 4 things too, even though the proof won't work at all. You need a completely different proof always, but yet somehow it like seems to be true a lot. And so I've been working with URA this summer, and indeed, it really does seem to be true for all of these shapes as well. So this is Marina Simmons. We can compute a lot of stuff, and we have parts of the proof. We have we have actually most of the proof, I would say. In particular, if we could deal with this shape here, then the other ones would be all taken care of. We're a little bit stuck on that one. Very strange. Okay. Do I want to say anything else? I think that might be all I was going to say. No, I was going to say a couple more things I don't understand at all. So I told you that like, suppose the thing you're expecting was a prime, then you're not getting that number, you're getting like some multiples of that number. I have no idea which multiples. Like before we had 11 and we had 33 and we didn't have any 22s and we didn't have any 44s. We just had like 11 and 33. And I don't know which multiples show up, and that's very strange. And in particular, I don't have any bound on like how big the multiples can be. That's like, That's pathetic, right? Like the first thing you want to know about this action is like, how big can it be? And I have no idea still. And then like, even if you knew which multiples showed up, they don't show up like with equal frequency. Some of them show up a lot more than others. Okay, so you kind of expect like the smaller multiples to show up more than the bigger multiples. That seems fine. But there's this weird preference for the odd multiples instead of the even multiples, right? Like 33 instead of 22. It's not that you don't get things like twice what you expected ever, but you get a lot more 3 times what you expected and more 5 times what you expected. There's a lot of like odd things times that. And I don't know what's going on. I don't know how you would prove such a thing, but and it's true for all the shapes. It's true for all the shapes, not just for the rectangles, but all of them. All right. Thank you very much.
I'm going to pause the recording. Thank you, Professor. Holy.